In the 11th lecture, we will cover the analysis of variance, including one-way ANOVA and the Bonferroni correction. Analysis of variance analyzes the differences among group means in a sample. It is a form of hypothesis testing heavily used in the analysis of experimental data. The ANOVA is a generalization of the independent two-sample t-test. Different from two-sample t-test, we only have one sample and use the concept of group in the ANOVA. It uses the ratio of between-group variation to within-group variation. In the ANOVA test, we first need to learn the concept of dependent and independent variables. The concept is frequently used in the ANOVA and the regression tests. The dependent variable is also called the response variable, outcome variable, or output variable. It is the model output and depends on the independent variables. The independent variable is also called predictor variable, explanatory variable, exposure variable, risk factor, feature, or even input variable. It is a model input and may cause a change in the dependent variable. In ANOVA, the dependent variable must be continuous, and the independent variable must be categorical. For example, we hypothesize students in different grades score the same in the exam. Then, the exam score is the dependent variable, and the school grade is the independent variable. Since the score is continuous and the school grade is categorical, we may use the ANOVA test as the analysis method. The ANOVA test has the following assumptions. First, the sample is a random sample. The observations should be independent to each other. The ANOVA test is not robust to violation to the assumption of independence. The results will be invalid if the assumption is violated. Second, each group is drawn from a normally distributed population, or the group size is sufficiently large. If the group sizes are equal, then we have a balanced model. If the distributions are symmetrical and unimodal, the model is balanced and all group sizes are equal than 10, then the test is robust and the results are valid. Third, all population groups have a common variance as the homogeneity of variances. For balanced models, if the ratio of the largest variance to smallest variance is less than 3, the results may be valid. The ANOVA test is not so robust to violations of the assumption, and we may need statistical tests to assess the data. The most common method is Levene's test. A p-value less than 0.05 indicates a violation of the assumption. If a violation occurs, it is likely that the non-parametric equivalent of the analysis is more appropriate. In the ANOVA test, if we have one independent variable, then we have a one-way ANOVA test. If we have two independent variables, then we have a two-way ANOVA test. We only study one-way ANOVA test here. One-way ANOVA compares the group means and finds whether any of the means are significantly different from each other. Thus, the null hypothesis is all group means are equal, and The alternative hypothesis is there are at least two group means significantly different from each other. Here, K is the number of groups. The sample mean y bar corresponds to mu, and y bar I is the ith group mean in the sample corresponds to mu I. The total sum of squares is the total sum of squared difference between the outcome and the sample mean, which is the sample variance multiplied n-1, where n is the sample size. We may partition it into two parts. The first part is the explained sum of squares, model sum of squares or sum of squares of treatment. And the second part is the residual sum of squares, sum of squares of error. The explained sum of squares is the sum of squared differences between the group mean and the sample mean. It represents the between group variation that may be explained by the group effect. Similarly, the residual sum of squares represents within group variation that may not be explained by the group effect. For a random sample, the sum of squares of the normal random variables is chi-squared distributed. The statistic f and m as a ratio of these two has a f distribution with n and m degrees of freedom. The mean of this distribution is m over m-2 if m is greater than 2, and the variance is this if m is greater than 4. We know total sum of squares follow a chi-square distribution with n-1 degree of freedom due to the Bessel's correction. The explained sum of squares follows a chi-square distribution with k-1 degrees of freedom, and the residual sum of squares follow a chi-square distribution with n-k degrees of freedom. The ratio, the explained sum of square divided by k-1 to residual sum of squares divided by n-k is the statistic f value. It follows a f distribution with k-1 and n-k degrees of freedom. In this slide, we have an example modified from the one used in the last lecture. We randomly selected 20 students from freshman, 20 from sophomore, and 20 from junior. All students took an exam and recorded the exam scores. We would like to know if students in different grades may have different performance in the exam. The freshman exam data is the same as the boy exam data in the last lecture, and the sophomore exam data is the same as the previous girl exam data. The ANOVA test may be used here with the score as dependent variable and the grade as independent variable. The null hypothesis is all the group means are equal, and the alternative hypothesis is at least one pair is not equal. Here, mu1 is the mean score of freshmen, mu2 is the mean score of sophomores, and mu3 is the mean score of juniors. The left table is the SAS dataset, and the three columns are the scores in each group. Since it is a random sample, the group sizes are equal and greater than 10. The sample variances of all groups are very close. we don't find the data violate the assumptions for ANOVA test. The SAS results using the ANOVA procedure are shown below. For one-way ANOVA, the model degrees of freedom is k-1, where k is the number of groups. Here k is 3 and the model degrees of freedom is 2. The total degrees of freedom is the total sample size n-1, which is 59. The error degrees of freedom is 59 minus 2, 57. The total sum of squares is the sum of the explained sum of squares and the residual sum of squares. The test statistic is the F value, and the null distribution is a F distribution with 2 and 57 degrees of freedom. The F value is 2.39 and the p-value is 0.1. Thus, at the 5% significance level, there is not enough evidence to conclude students in different school grades may have different exam performance. In the last lecture, we tested the null hypothesis mu1 equals to mu2 using two sample t-test. The t-statistic is 2.12 and the p-value is 0.041. Thus, we rejected the null hypothesis. In this lecture, we have the same data for the first two groups, but we cannot reject the null hypothesis. These two results seem contradictory. The discrepancy is not due to the different tests. We may use the ANOVA test to test the null hypothesis mu1 is equal to mu2, and we will have the same p-value of 0.041, and we reject the null hypothesis. Thus, what causes the disagreement? For the research question that has more than two groups, if we use two sample t-tests, then we need multiple comparisons. If we have three groups as the example in the last slide, then we need three comparisons as shown in the alternative hypothesis. We need to compare mu1 and mu2, mu1 and mu3, as well as mu2 and mu3. If any of them is not equal, then we will reject the null hypothesis. Let's say they are in fact equal. When we compare mu1 and mu2, if they are in fact equal, then there is 95% chance the result is negative since the significance level is 5%. Thus, the chance that all three comparisons are negative is 95% to the power of 3, which is about 85.7%. Since we will reject the null if any of the three tests become significant, then there is 14.3% chance that we reject the null hypothesis. The type 1 error increases from 5% to 14.3% if we use 3 two-sample t-tests for the hypothesis testing. Thus, multiple comparisons within one research question may increase the type 1 error. When the research question involves multiple comparisons, the ANOVA test put all groups in one model and conduct one test. Thus, it is better than the multiple comparisons. In general, when we have the following hypothesis, then we need k multiply k minus 1 divided by 2 tests and will dramatically increase the type 1 error if the significance level is not adjusted. The controversy of the results in the last slide is caused by the research question. Both t-test and the ANOVA test results are correct, but they are for the different research question. When we are only interested in one comparison, we will reject mu1 equals to mu2. But if we are interested in more than 2 groups and any one comparison may fail the null hypothesis, then the ANOVA test is more appropriate. In some cases, we need to conduct multiple comparisons to answer one research question. Then, the Bonferroni correction offers a simple conservative approach, which sets a new alpha equal to alpha divided by the number of tests. The key question here is whether or not we need to apply the correction. The answer is related to the research question. We should not just apply the correction just because we have several models. In summary, we learned the one-way ANOVA and the Bonferroni correction. In ANOVA tests, the dependent variable must be continuous. The independent variable must be categorical. The valid ANOVA test is based on the following assumptions. The sample is a random sample. Each group is drawn from a normally distributed population, or the group size is sufficiently large, and all groups have a common population variance. One-way ANOVA compares the group means and finds whether they are significantly different from each other. The f-value is the ratio of the explained sum of squares divided by k-1 to the residual sum of squares divided by n-k. The statistic follows a f-distribution with k-1 and n-k degrees of freedom. For the research question involving multiple comparisons, the ANOVA test is ideal since the ANOVA test puts all groups in one model and conducts one test. If we cannot avoid multiple comparisons, then the Bonferroni correction offers a simple conservative approach, which sets a new alpha equals to alpha over nt, where nt is the number of tests.